Last unit for chapter number 15, manipulating chemical equilibrium expressions, disturbing the chemical equilibrium systems, and then predict what is the direction for reaching equilibrium after the system is disturbed. And with that, we have the sharing of the screen. And here we come to the third part of the unit here. So the content for this particular unit, the last unit, are as follows: relating the different chemical equations for the same chemical reaction, correlating the old equilibrium constant with the new equilibrium constant Kc, net expressions for a series of equilibrium reactions, Le Chatelier's principle, and disturbing a system in equilibrium. Before I proceed, I need to tell you that the master slides, there may be a large number of master slides under the PowerPoint presentations outside of this topic content. Furthermore, please do take assistance from your audiobook for this particular course so that you don't miss out on anything. As stated before, I'm just focusing on the most important topics that a student needs to know in order to proceed on to the next section that is there, or in order to understand. Because at the end of this particular section, we will start chapter number 16, which is a second part of chemical equilibrium with aspects in acid and base, acid-base chemistry, that is to be known. So here, now, relation between various balanced equations and equilibrium constants. Basically, what it says is we are going to be manipulating the equilibrium constants, and we want to know how to get the relationship, multiplying the coefficients of a reaction. So we have that S solid sulfur plus 3/2 oxygen gas gives you SO3. That is one equation, and this is the old equation. And you get a new equation, 2S plus 3O2 gives you 2SO3. If you look at the first equation, the old equation with the new equation, all you're doing is multiplying it by 2. And therefore, we see that the general relationship is K mu is equal to the equilibrium constant for the old reaction raised to the number, raised to the coefficient n, which is the multiplying factor. Next, if you reverse the reaction, what happens? What is the relation between the new K and the old K? And the reactions are shown. 2S solid plus 3O2 gives you 2SO3 gas. 2SO3 gas breaks down to give you 2 sulfur solid plus 3O2. If you look at it, the second equation is just the reverse of the first, and therefore the general relationship is K new is equal to the reciprocal of K old. Then, when you add up reactions to get a net reaction, in this case, we are doing the reaction in multiple steps. S solid plus O2 gives you a reverse reaction, SO2 gas. SO2 gas combines with half an oxygen gas to give you SO3 gas. So the net reaction is S plus 3O2 oxygen gives you a reverse SO3 reaction. And so we find by just looking at these two sets and multiplying them, we get that K1, the K net new reaction coefficient is a product of the individual K's values that you have. So after this, you have a study concept equation, a study concept equation. So there are two problems to ensure that you have understood how to solve the relation between old and new equilibrium constants for a given chemical reaction. The next one is Le Chatelier's principle. Le Chatelier's principle is generally primarily applied to systems that are in equilibrium and you disturb the equilibrium. Now, when the disturbance to the equilibrium system occurs, then the system always moves in a direction that is opposite to the stress disturbing influence. And if possible, at the end, the system will try to return back to its equilibrium. If the conditions of a system initially at equilibrium are changed, the equilibrium will shift in such a direction so as to restore the original conditions. And this is the basic concept of it. Now the question comes, how can we disturb the chemical equilibrium? We can disturb the chemical equilibrium by changing the temperature, changing the concentration of the reactant or product, changing the volume or the pressure for gaseous systems. A change in any one of these factors will disturb the equilibrium condition, causing the system to move in such a manner as to reduce the effect of the change produced. Now, so using the three factors that are there, temperature, concentration, volume change, we have the next few slides explaining what would happen. So remember that in thermochemistry, you learned that the reaction can be endothermic, absorbs heat, exothermic, releases heat. So for an endothermic reaction, the best one of the examples is cobalt chloride equilibrium in water. In the presence of an acid is pink in solution. When we add a base, the solution turns to blue. And this is an endothermic reaction. And so if you increase the temperature, the question is, how does the equilibrium shift? Part of the heat energy that you supply is used to counter the changes, the rise in the temperature, and the remaining part is distributed in order to counter effect the direction change. And so in this case, when you increase the temperature, equilibrium will shift to the direction that is endothermic, because it uses some of the added heat energy to counteract the temperature increase. On the other hand, if this reaction were to be carried out under lower temperature, the equilibrium will shift in the direction that is exothermic, produces added heat energy to counteract the temperature decrease. And so this is a self-study question where you have to answer what happens. You have the ferrothiocyanate reaction, which is a red-brown color solid that is there. And the chemicals that are added are iron chloride, potassium thiocyanate, and a neutral compound. And you have to explain what the changes would be. So that's a good question. Next, what happens when you add increase the concentration of a particular reactant? In that case, again, we see the concentration of the second reactant generally tends to get lowered. The concentration of the product increases, and increases in such a way that the K remains constant as long as the temperature is not changed. What happens if you remove a particular component from the reaction before the reaction mixture starts? If you remove a particular amount of a reactant before, then what happens is, again, the concentration of the reactant removed decreases, the concentration of the second reactant increases, and then, of course, steadily the concentration of the product increases in such a way that the equilibrium constant K is maintained a constant. Increase in pressure. Now, these are for gaseous systems, and so we have the moles of gaseous reactants. So the effect of pressure and volume are inverse to one another. You have to remember that because the ideal gas equation states that PV is equal to nRT. Therefore, the partial pressure P is N over V times RT. N over V, by definition, is the molarity of the solution, or moles per liter of the reactant. And therefore, the reaction, if you increase the pressure, thereby decrease the volume, then the equilibrium shifts to the side with the lower number of moles of the gaseous reactant or product. If you decrease the pressure, then it goes to the side which has the larger number of moles of gaseous reactants or product. And here, this is a self-study problem where everything is introduced, whatever you have studied to date, with the factors disturbing the equilibrium, you get a full set of questions, and so you can sit and practice it. Now, one of the applications of Le Chatelier's principle is the production of ammonia in the Haber-Bosch process. We find that in the Haber-Bosch process, nitrogen gas reacts with hydrogen gas to give two ammonia gas. The delta H at room temperature is minus 92 kilojoules per mole. At 400, it's an exothermic reaction rising up to 105 kilojoules per mole. So you have to explain what are the conditions of temperature and pressure which will maximize the yield of ammonia. We said that the total number of moles of the reactants is greater than that of the products. So thus increase in pressure will favor the reaction because it's going towards the lesser number of moles. But at very high temperatures, because it's an exothermic reaction, it will start decomposing. So you have to maintain a balance between the two to get maximum yield. And now, when the components come out, all of them are in the gaseous form, but the boiling point of nitrogen and hydrogen is very, very low as compared to that of ammonia. So if you pass the mixture through a cooling tower, nitrogen and hydrogen remain as gases, ammonia condenses to a liquid, and the nitrogen and hydrogen gas can be recycled and passed over the catalytic converter and continue the process without stopping the plant. And here is a setup of the plant that you have. And you can see that the whole setup, you have the catalyst, and nitrogen-hydrogen gas is pumped initially through the top of the tower, passes over the heat exchanger, gets warmed up, passes over the catalyst, and goes through the mixture, heating coil to get warmed up. Once it gets warmed up, it passes through the catalyst over the heat exchanger, goes through the cooling chamber, ammonia gets liquefied where the remaining gases go through the recirculating pump and passes into the system again. And the whole process continues repeatedly. Another application of equilibrium is the oxygen transport by blood using hemoglobin. At sea level, the partial pressure of oxygen is 0.2 atmospheres, while at 10,000 feet it is 0.14 atmospheres, so that at higher altitude the pressures are lower. Therefore, you find in people living at high altitude, they have a higher concentration of hemoglobin in their blood so as to retain the required amount of oxygen they need. And so when they come down to sea level, they have very high concentrations of oxygen in their blood system. And therefore, athletes, when they train for long distance running and for fast running, they generally train at high altitude for months so that the hemoglobin count increases, and therefore they can do perform better. Now, the self-study and review concepts. In this particular problem, we are basically using chemical kinetics and chemical equilibrium to solve and ensure that the net reaction gives a rate K is equal to H2O2 raised to the power 2 and I minus. The reaction consists of two-step. It's a two-step reaction. One is very fast and the other one is a slow reaction. The fast reaction attains equilibrium quickly, and the common ion species that is produced in one reaction is used up in the second reaction. And so the net reaction, if the K values are given, all you have to do is multiply and you get your answer. Now there are, again, a couple of self-study questions using different conditions. So please go through that. And once you finish that, at the end of it is the introduction to chapter 16, acids and bases and chemical equilibria in aqueous solutions. And the content consists of, the content is, what we will do in this is recognize common monoprotic and polyprotic acids and bases, write balanced equations for the ionization in water, recognize the Bronsted acid base in a reaction, identify the conjugate pair of each, identify the acid base reactions undergone by amphiprotic substances. And with that, I'm going to stop the share.